Okay. This is SWAT cup interface. Okay. What is the input for this SWAT cup? Whatever the output coming from the SWAT, that will be the output input to the SWAT cup. Okay. All of you open SWAT cup. And there one green color cup box will be there. Click on that. Okay. Click on new project. Click next. Here we need to browse the text and out folder location. Okay. Click on browse and go to your ArcMap project folder. Go to your path where you have saved your ArcMap project. Okay. Wait. Okay. I think you have saved the scenario with some name, right? We have saved with sim1. I think you might have saved with some other name. Okay. And see this pink color one, text now. Okay. Select that one. Click open. Click next. Here you need to choose the SWAT version. Latest version we need to choose SWAT 2012 and processor. If you are using 32-bit, you choose 32-bit. Or else if it is 64-bit, you choose 64-bit. If it is 64-bit, you want to choose 64-bit. Okay. Click next. And next. Here we need to choose our project folder. Okay. There one folder will create. And all whatever the results will come in, all those SWAT cup results will be for in that folder. Okay. Go. Oh, this is not project type. Okay. Here it is project type. Here these are the different algorithms which were inbuilt in this SWAT cup. First one is SUPI2, glue, Parazole, Monte Carlo, PSO. Okay, particles of optimization. So from the literature review, it is observed that when you are looking for a stream flow or sediment yield, for these two, like SUPI2 algorithm is giving best results. Okay, so that's why we are choosing SUPI2. Select SUPI2. SUPI2 sequential uncertainty fitting algorithm. Okay. Next, just create one project name. Just type cup 1 or something. Okay. Next, give project location here. You need to create one folder. Just create one more. Change cup 1. Okay. Double click on that. Click OK. So all the results of SWAT cup will be stored in this folder. Okay. Next, finish. So whatever the text and out folder there, it will copy paste in this folder. So it won't disturb the original one. Okay, now whatever we are doing, file and errors, all will done here. Okay, all of you reached here. Now we copy paste on the SWAT text and out folder here. Now we need to tell the SWAT cup, so where my watershed outlet is there. Okay, here we need to give our observation data because in the text node folder there is a simulated data. Here we need to give observation data, everything. Okay, so first step is calibration inputs. All of it click on reach. So we are doing on a reach level. Okay. Next, calibration inputs. The first one is parameter information. Okay. Here, the basically 4 parameters are there. Okay. We need to add some more parameters. It was like almost 21 to 25 parameters are there related to stream flow. Those we need to use. Okay. I will explain how super tool will work. Okay. So what super tool does is it will follow Latin hypercubic sampling. Okay. It will follow Latin hypercubic sampling. So Latin hypercubic sampling means, for example, here one parameter is there. Okay. We need to give parameter and we need to fix the range. Okay. For example, 1 to 100. Okay. 1 to 100. For example, x parameter ranges we have given 1 to 100. Suppose 1 to 10. Y parameter we have given range 1 to 10 again. Okay. So 2 parameters range we have fixed. So what a Latin hypercubic sampling, what it will does is, suppose we gave 50 iterations. Okay. It will divide the x range into 50 equal intervals. Okay. 1 to 10 is a full range, right? It will divide the 1 to 10 range into 50 equal intervals. Okay. Means what? Suppose if it is 1 to 100 means 1 to 5, 5 to 10, next 10 to 15, 15 to 20, 20 to 25. Like that, it will divide the full range into 50 equal intervals. We have given 50 simulations, 50 iterations. In the same way, it will divide the second parameter range into 50 equal intervals. Okay. Then what it will take is, it will identify the unique parameter set. Okay. From 50 equal intervals, from each interval it will take randomly one value. For example, first equal interval is for x 1 to 10, 1 to 5. So it will randomly pick one value. Again, in the second parameter, in one of the interval it will suppose in the second interval also 1 to 5, it will take randomly one value. Okay, so that will be one unique combination. So model will run with that unique combination. Understood? In the similar way, how many parameters you have given? For all the parameters, it will divide the full range into that many number of equal intervals. How many you have given iterations? Okay. After that, it will identify the unique parameter sets. Then it will perform for the each parameter set. Suppose if we have given 500 iterations means it will identify 500 unique parameter sets and model will run 500 times. And it will tell you out of 500 parameter sets which parameter set is giving best results. Means out of with respect to all those 500 simulations, the 50th or 60th, whatever it is, that particular number simulation parameter set is giving best match compared to remaining 500. Okay, this is what whole super tool does. Now we will see one by one. Okay, first we need to fix the parameters and then we need to give the parameter ranges. Okay, first we will fix the parameters. For example, first parameter is CO2. There are almost 21 parameters are there which is related to stream flow. So there are some. So suppose if you want to add some other parameters, some other important parameters also there. Okay. Go to add new parameter, the plus symbol. And one of the most important parameter is soil water availability. Okay, soil water availability capacity. So that will be there in soil related information. That is soil related information, right? So it will be available in the .SOL. And these are the soil, you can say characteristics or parameters, or the soil related parameters. Here we are taking soil AWC, available water capacity, soil available water capacity. It is also one of the most important because based on the available water capacity, for example, what is available water? Field capacity minus melting point, right? So if there is a more space, so more water will occupy. So surface runoff will be less. If that depth is less, then available water capacity depth will be less. More surface runoff will happen. Okay. So that's why it is also one of the important parameters. We have added that soil. Just click OK. And one of the more important parameters is soil hydraulic conductivity. Soil K. Just similar way, go to add new parameter. Just search for soil K. Just below the soil AWC. Okay. Click OK. Okay. We are just taking for the today's just answer. We are just taking 6 parameters. Otherwise, it will take time. Okay. 6 parameters. And next one is we need to choose the method. So how we are adjusting your parameters with respect to the baseline period? Are you replacing the value with the initial value? Are you adding the value with the initial value? Are you multiplying the? Are you increasing that with relatively? Okay, that we need to choose. So just keep cursor here. Method. Just keep cursor here. Just keep cursor here. And question mark. Question mark. Okay. Fine. I will help. Yeah. Just arrow mark down arrow. So there are 3 methods, right? Relative, absolute, and replace. So what will happen exactly? I'll tell you. So before we are performing calibration, we need to look into all these parameters for the uncalibrated model. What is the CO2 value? If we run the model, what is the CO2 value? What is the soil AWC value initially? Okay, those parameter values we need to note down. What are the initial values? Okay, then CK. R relative means multiplies the existing value. For example, I'll tell relative later. Second one, additive. For example, our groundwater delay. Okay, suppose initially it is 10 days are there. Then we are adding, suppose here we will keep the range 15 to 30. After 500 iterations, we got that the best value 1 will come. Suppose it came 20. Okay, if you keep additive means what will happen? Initial value is 10, right? 10 plus 20. So value become 30. So for that 30 model will run. If you keep replace method, that 10 will become 20. Okay. If it is a relative method, what will happen? Relative means it will change minus 100% to plus 100%, right? So it may vary from minus 1 to plus 1. Okay. So, for example, you got the value after 500 iterations. After 500 iterations, after 500 iterations, you got value is between minus 1 to plus 1 you will get. So, for example, you got 0.5 value after 500 iterations. 0.5. Okay. What it will do is 1 plus 0.5. It will become 1.5. So that 1.5 value will be multiplied with the initial value. For example, initial value is 70. 70 multiplied into 1.5. Whatever the output comes, that will be taken for the model run. Understood? For example, I'll tell one more time. It was somewhat tricky. Yeah, I will tell. I'll come to how to fix the range. Okay? You understand these 3 methods. First one is replace. What will happen? Whatever the value which is coming after all the simulations. So that particular value will be replaced with the existing value. Okay. If you have choose additive method, whatever the value which is coming after the simulations, it will be added to the initial value. If you choose relative method, what will happen? Whatever the value which is, when you are choosing relative method means that particular range should be in between -1 to 1. So we will get one value. Suppose you got -0.3. Okay, after all iterations. So 1 plus -0.3 will become 0.7, right? 0.7 will be multiplied with the initial value. So value will reduce. 70 into 0.7. Value will reduce. That reduced value will be used for the model run. Okay? Understood? And for which parameter, which method should be used? That is also one of the main criteria. Okay? Which method want to use? For example, CN2. CN2, why we have to use relative, and when we need to use replace, when we need to use additive. Okay, that you should also have that clarity. When your parameter is varying with respect to HRU. For example, this curve number will be depend upon the crop type. Okay, so these crops will be vary from HRU to HRU. When your parameter is varying with respect to HRU, then how to choose relative method. Okay. When your parameter is constant throughout the subbasin, then you can choose either additive or replace. Understood? Should remember this. When the parameter is varying with respect to HRU, then you have to choose relative. When the parameter is same throughout the subbasin, then you have to choose either replace or additive. Okay. For example, what will happen if you choose replace method or relative method for a curve number? Okay, what will happen for each HRU? For example, in one HRU, CN value is 50. In second HRU, one is 70. In the same subbasin, in subbasin 1. So if you try to replace these two, suppose you got 60. Suppose you got 60 after 500 iterations. What will it do? It will replace 50 by 60, 70 by 60. Then that spatial variation will go on. Okay, that's why we are using relative method. So relative means this value will vary from -1 to +1. For example, after 500 iterations, you got -0.3. Okay, 1 minus 0.3 will become 0.7. So what will update is 50 into 0.7, 70 into 0.7. Still you are maintaining that spatial variation. Okay. So you just keep in mind that when the parameter is varying with respect to HRU, use relative method, and when the parameter is same throughout the subbasin, use replace or relative method. Okay? In such a way, you need to choose this method. So, as per the literature review, like all the groundwater parameters, like we have seen, the SWAT was not able to capture all the groundwater spatial variations. So it's what SWAT will assume that throughout the subbasin, groundwater parameters are same. Okay. So this alpha BF is base flow. So use it is also groundwater parameter. So all the groundwater parameters, they are not changing with respect to subbasin. So you can use either additive or replace. So choose replace method. For groundwater delay also choose replace method. Just change that method. Okay. Groundwater QM it is also groundwater parameter. Here you can see dot GW means groundwater parameter. Dot MGT means management parameter. Dot SOL means soil parameters. This soil is also varying with respect to HRU, right? So soil is also have to use the relative method. Understand how to choose the methods? Now we have to fix the range. For relative, anyway, that range will be vary from -1 to +1. Okay, but you should not give blindly -1 to +1. That is the full range. will happen? It will do 50 into G, like 0 to it will check. It will test the CN value 0 to 100. So it will take broader range. So that means calibration will take time. So that's why in the calibration, these parameters should not, it won't change much. Okay, 50 suddenly won't become 10, 20. 50 might become either plus or minus 10. That's it. So it won't become 0, it won't become 100 suddenly. Okay, so the variation might be plus or minus 20%, not more than that. Okay, so that's why we are keeping the first rise minus 0.2 to plus 0.2. Okay, for CN2. Next, alpha BF. Okay, alpha BF means base flow. How much time it is taking to create to reach the base flow to the stream. Okay, this is you keep either 10 to 15 days. 10 to 15. First one, alpha BF. One more thing I want to tell you. Suppose you just click on this one, absolute SWAT values. It will, this, here all the parameters are there with the full range. Okay, if you don't know what is the range of parameter, here you can check. But here the range, it is full range. Here whatever it is giving. Okay, you can check the parameter ranges here, initial ranges, broadly from like starting point to ending point. Okay, next coming to groundwater delay. Just keep, I think, keep 100 to 150. Keep 100 to 150. That's what. This arc map is not working. Actually, if the arc map is working, I think no need to do arc map. Huh? Okay. I'll tell you. Okay. Open desktop. Scenarios. Scenario. Text now. Text now. Come on. Text now. Open gw.jw. Open notepad. See here, whatever the model which we have run, initial model, in that it was mentioned that groundwater delay is 31 days. Okay, these are the values you should note down before giving the ranges. So according to that, we will change the ranges. Now, what are the parameters I am giving now? Groundwater QM. Open it. Groundwater QM. Open it. What is the initial value? And you can see the definition. Threshold depth of water in the shallow aquifer required for return flow to occur. Okay. So you will, it is initially 1000 mm is there. Just fix that. So how you need to fix the range is, for example, what our model is predicted, it is predicted over predicted, right? So we need to decrease the surface runoff. We need to decrease the stream flow, right? So you need to know the relationship between each parameter versus stream flow, surface runoff. Each parameter with respect to surface runoff. For example, curve number is directly proportional to surface runoff, right? Now what you need to do, our aim is to decrease the stream simulated flow, right? Because it is overproductive. So we need to reduce the surface runoff. So surface runoff was directly proportional to curve number. So curve number should be decreased. You can see, open .mgt operations. What is the initial value? Minimize it. Go to scenarios. Open init.mgt. Go first. Type you can search also. value 25.5, the value of curve number is 77. So what we need to do now? Our aim is to decrease the curve number so that it will, because it is directly proportional to stream flow, surface runoff. So, okay, just minimize it. Minimize it. That one. Now here, just keep it here. So what we have kept to minus 0.2 to plus 0.2, right? This is our initial range. But we have a clarity that we are decreasing the, we should decrease the surface runoff. So if you want to decrease the surface runoff, it should come negative, right? Because we are using relative. It should come negative. So no need to keep positive here. You can keep minus 0.1. Understood? Why we are keeping, why we are limiting to only negative range? Because if you keep minus, just keep minus 1 here, minus 3 to minus 0.1, minus 0.3 to minus 0.1, minus 0.3 to minus 0.1. So even if you run 100 simulations or how many number of simulations, the output should come in the negative, right? So the negative value will be multiplied here, the curve number will decrease, automatically stream flow will decrease. In the same way, you need to identify how the each parameter is relation with the stream flow. Okay, alpha BF, base flow. Base flow is the inversely proportional to stream flow. The base flow is very, it was immediate response, so surface runoff will decrease. In the same way, soil hydraulic conductivity. If your soil hydraulic conductivity is very high, so that means what? Runoff will be less because soil is having high infiltration. So runoff will be less. So you can also check what is the value of soil hydraulic conductivity for the model which we have run, and we need to increase that hydraulic conductivity so that our stream flow will decrease. So if I want to increase hydraulic conductivity, first you should know what is the value initially there. Just check